Assalamualaikum. Good afternoon to all. This is a topic on the discrete time system. The last topic on process control, advanced process control. This is the system when you have a digital computer control loop. If you look at it, most of it is very similar to what we have seen, except a few components here that we can see clearly. Basically, the final control is the same, process is the same, we have the measuring element. This is basically part of the measuring element, but when you go into digital, it means it's done by computer, which is actually normally the case, where the controller is a software based, so you have to go into what you call a sampler for it to be discretized, put into the discrete signals and converted to the A to the analog to digital numerical values. It goes to the computer, okay, to the simulation or the controller action, and come out or have to convert from digital units, binary to analog units. Then it has to be whole to make it continuous. Then it goes to your electro-pneumatic converter if necessary. It may not be, but if you have electrical, you have a pneumatic here, then you have to go to electro-pneumatic converter, and then goes to the final control element like the valve and do the process and so on. So basically in digital system we have this extra element. Basically the two extra element, one's a sampler and one's the whole element. That makes it different from the normal continuous system that we have seen so far. So that's why it comes under a very slight advanced control method. But it's just in the configuration side. In terms of the methodology, in terms of the theory, very similar, as you will see later, in discrete time signal. So these are all discrete times. D is all discrete time signal, and C is the discrete. D is the discrete time. C is the continuous. In all is continuous. This is a discrete time because all these are basically inside the computer itself. This is one signal. Many signals coming in like the real world, many outputs going in the real world, and you have all these different inputs, and what we call have multiplexer to take in the signal by signal, and as it goes, sampler means to convert into the discrete signal and so on. The others are the same, and again when going out, we have another multiplexer to go to the different converters and different final control elements. So this is just a normal real world application where you have multiple inputs coming in, multiple outputs going out. So the most important thing is to convert that continuous signal into basically a discrete signal in a discrete time system. This is the whole, this is just a step. Normally it's just a step, but we basically convert to discrete signal, and this is where we use delta function, direct function you have seen before, or the impulse unit. So this is the theoretical function which is being used very heavily in this discrete times subject. And as you see, so when the t tends to 0, okay, h tends to 0, you get the impulse function. From pulse to impulse, this is how it is being formulated as we have seen before. So this is the main impulse function that will represent the discrete time system. Yeah, this is one that represents discrete time. Continuous function that we normally have. We want to convert into the discrete time, so we convolute it on we use the sampler with the direct function. This is a direct function with equal signals, of course, but this is the magnitude depends on this signal. So once you convolute this with this, you will get this discrete time signals, okay, depending on the magnitude at that point where you sample it. So this is called a Y star, different signals at different time. And so this will be the discrete signals that we have got after going to the sampler that will be processed by the computer and the digital system. So how do you formulate the equation? Basically, can be done in terms of using the impulse function again. The Y star, the discrete time, is the continuous, and convolute with the impulse function or the direct function, we call it, and so we get a sampler for one signal. But you have a sequence of signals, so the sequence of impulse is just the signal at this time 0, the second sampling time, third sampling, and so on. You just add it on summation, and you get y not delta t. Okay, this is actually not the discrete time, so it should not be a the star here should not, it doesn't have a star actually, it's just a y dot, like this y dot, sample at this time, yt sample this time, and so on. Okay, y star means it's already being sampled, equals of input. So when finally what we get from here is the y star summation of y and t, the direct t n minus t. So this is going to be the equation that represents the sampler for different times and so on. So this is the main equation that will be used in the discrete time system, but we want to convert into a more what you call general system like we have before in terms of. So again, yeah, continuous the sampler. This is what when we take the Laplace of both sides, okay, we'll get this Laplace, and when we simplify it, we will get this function, and this is just one. So this is going to be your Laplace transformation of that sampler formulation. So expect it presents the sequence of impulse coming out of the impulse sampling in the S domain. So this S domain, but in discrete time we don't work in S domain, we work in the domain, which is defined by this term here, summation y and t and z minus n. Z minus n is the sampling time. So when we compare just now 3 and 4, what we can say is that the z transformation variable is equivalent to e to the ts, which is sampling time, and the s transformation variable. This is the relationship between the s domain and the z domain. That's all. Okay, so we don't know in s more for the continuous, z for discrete time, but the relationship is there. So basically, when what we get is a z transformation of yt is basically just this one here, as we've seen before, summation of the signal from 0 to infinity. Okay, infinity means a certain time at a long time. The y value at that sample time times the z minus n. Z minus means this is the this z transformation at the different times. At z minus n at the different times, and so on. So in conclusion, the Z transform of sequence of sample values is a special case of the Laplace of the sample sequence of impulse where related by this Z equals e to the ts. Okay. What are the differences? The Z transform maps discrete time signal from time domain to Z. Okay, not to Laplace, to Z. The Z transform depends on the selected value of the sampling period. So it also depends on t, the sampling time. It's important because it's discrete time. Definitely depends on sampling time. And if two distinct functions have same sample values at the sampling instant, they also have the same Z transform. It cannot be distinguished. So if at that time you get the same signal value, you cannot distinguish it. Although the shape may be different, but at that time the signal is the same. When you say as Z transform, the shape, the values will be the same. That's the issue that we have to sometimes take care of. And Z transform exists for those values of the independent variable Z for which the summation of infinite terms takes finite. Of course, the infinite term have to take finite values for it to exist using the Z transformation. The example of a Z transform unit step. Okay, unit step is just 1 plus Z minus 1 plus Z minus 2. Okay, and if you combine it, you get this 1 Z minus n Z minus n, and this is basically the Z transformation by itself. And if you simplify it using the finite value series, you get 1 over 1 minus z1, which applies as long as z minus z1, this one has a finite value. So unit step is just this. This is how you formulate the unit step in terms of this, and that itself is already the Z transformation. Very simple. Okay, so you can put it either in this form or you can put it in this form. There are two ways of putting the Z transformation, either in Z minus 1 or Z. Some people prefer Z minus 1, some prefer the Z, some Z minus 1 is easier to visualize the delay. Z minus 1 means the delay at one time, Z minus 2 delay at one time. So sometimes it's easier to visualize. But sometimes you put in this form for mathematical. For RAM function, you get this is a Z transformation. How you get when you formulate this RAM transfer function in discrete time, this is going to be the values. The 80 at Z minus 1, at 2, at Z minus 2 seconds sampling is 280, the magnitude. At third sampling is 380. So you simplify it, you get Z minus 1, and this itself is already the Z transformation. Okay, I have to put in terms of Z minus 1 or Z form. This is Z minus 1. So it's this, as long as this is less than 1, you get finite value, you have a Z. So the properties of Z, just as before, in S we got a few properties that's similar. They are linear properties. Z transformation of A times F1 plus A2 F2 is just A times Z transformation of F1 plus A2 times Z transformation of F2. We have translated function, means it's a function delayed by TD time. It's just Fz. Z minus KD represent the delay. In this case, we assume TD is equals to a multiple of the sampling time, KT. K can be 1, 2, 3, and so on. So this sampling time, K means how much sampling time. So we assume that the delay is a you can put in terms of multiple of sampling time. You have to, because there's no in between. In discrete, it's just take value at different sampling time. In continuous, can be any time. In discrete, so we assume it's closed. So this is the translation. If you want to get initial value, you put in this form, y z to infinity. For final value, you put in this form to get the final value. As we've seen before, for continuous, we have the same thing to get the final value, the steady state error, and so on. We use this theorem. Okay, then if you, in terms of inverse, you want to get that you have done the z, you want to go back to inverse. There are few ways of doing it. Either you get straight from the table. Okay, that from the table, you have the table. You can, if they're straightforward, you can just pick it up. If there's a longer function, then you have to break it down into z minus 1, then break it down to partial fraction as we've done for the s, and then put solve for c1, c2, and go back and find out what is the z transformation from the table. This is just a minus half step function. This is exponential value, it's 1.1. Okay, this is the, but another way of doing it, which is long division, tedious but simple to get the z transformation. Basically, you just divide this by, you divide z minus 1 by this one. This is what you're going to get, and this itself is already the inverse inverse z transformation, and this itself will tell you many things, because z minus 1 is the delayed time. So magnitude at z minus 1 is just 1. This is the delayed time. Magnitude at z minus 2 is the second delay or second sampling time. The magnitude is 4, and so on. So you can, from here you can pick up the magnitude. 0, there's no value at 0 time. Initial time is just 0. So this is the most straightforward method of getting the inverse, by just doing straight long division. It's a bit tedious, but it's so easy, and you can get up to whatever value you want to get back the magnitude at the different time. And then you want to know what is the magnitude at the different time sample that you want. So this is an inverse, but still within the sample time. Okay, you cannot really convert it back to the actual continuous in Z transformation, but you can get it at the sample time from Z to KT values based on KT or NT in this case. Okay, so you want to get the transfer function for discrete time. Is basically the same way as before. Only thing we now add on a whole element. Normally we'll have a whole to go to the, because this is discrete, so we want to go back to the continuous. You have the whole element. The whole element transfer function is given by this. Okay, so you take the discrete time, is just taking the z transformation of this transfer function. Is just yz over cz equals to hgpz. So yz over cz hgpz is just z transformation of hs times gps. Okay, and if you want to get the inverse, it's just z minus 1 hgpz. This is cz. Okay, and this is different from, it's not the same as hgpz equals to az gz. No, this is z transformation of h times gp first, hs times gps, then take the z transformation. If you put this, it means you are taking the z transformation of h, z of transformation of g, and then you multiply it. So it's not equal. This means this time this, then z transformation. This means z terms of h and z terms of b. So normally it's just combined together, because these are still the whole element related to the process. So we combine them, take that, combine them, and multiply them, then only take the z or z minus 1, whatever we want. Okay, so example, if you have first order with a RAM system, KPOS here. Okay, so we just combine them, do it separately, do the KPOS squared and KPO this one. Okay, and then get the Z transformation. This is the Z transformation from the table. Combine them and you get a simplified Z transformation of H GP. I mean this H times GP, and take the thread transformation. So this is called a pulse transfer function, or basically a pulse means in discrete time, or in this case, in terms of transfer function means in terms of Z domain. Like in the continuous, transfer function means convert into the Laplace domain. In this case, transfer function means the discrete function means convert into the. And the other one we need, basically the two functions in discrete time that we introduced from the continuous, the sampling, change it to discrete signal, go to the computer, formulate, simulate, whatever, calculate and come out with a signal that is coming out is a discrete. But to go to the continuous, we need to make it continuous. We have to hold it. So this is what's happening. Discrete signal, you go to the data whole step, you're holding the signal K0 for some time to the next sampling time. Okay, that's what's happening in visually, and in terms of this is how you're going to derive it. At time 0, you get a K0 into that whole element. You can convert the X discrete value to K0 times the impulse function. At the first time interval, you're going to get the step function, so it's just K0 ut minus ut minus the sampling time, and similar for every step. So you get for inputs, it's a combination of all the input sequence. So x star t is just a summation of kn dtn minus dt. This is extended to for all signals, so it's summation, and this for all signals in this way. Okay, k naught ut minus t plus the k1 at the next value, the k, and so on. And then you get a summation of kn utn minus t minus utn t minus t. You take the Laplace of the input signal, you get this. You take the Laplace of this output signal, you get this. Okay, and then if you divide this over the element Laplace transfer function, which is given by this, as I showed you before. Okay, well, I don't need you to go into detail and memorize all these things, just to know roughly how to get this one. Okay, how do we get the whole element transfer function? That will be used in our closed block transfer function. So if you have the discrete time analysis, this is what you're going to do. Same as before, the only thing we add the whole and we add the sample values. Okay, so these are the discrete time values, the LZ, the CZ, the YZs that you have sampled. Others are continuous, YS, MS, motivated variable, the disturbance are continuous. These are whole element, process element, GD, that's all continuous. And discrete is the controller is discrete itself. There's a slight difference from what we have seen before, like continuous PID, adding this extra loop that we have to add in because we are discretizing it and putting it into the software which acts as the controller. Then it's still the same. You get y1 plus y2, the main process output difference of the effect of disturbance. Take the z transformation of y1 is just hgp z zz, and take the z transformation of y2 is z gd ds. So we just normally leave it as it is because we cannot define gdz for the disturbance because disturbance is not a sample value. Disturbance is continuous, so we leave it as it is for the disturbance side. But for the we formulate the for the main process output, this is what we're going to get. So we HGPZ budget, this is the whole output y from the main motivated variable from the disturbance side. But EZ is RZ minus Z, that's so we can simplify CZ equals to controller times EZ in this form. Okay, so we get the controller the transfer function here. If you simplify it further, you get this as the main output value HGP DZ RZ, which is set point minus the sample output plus and so on. So similar to what we've seen in the continuous, only thing is now in Z domain and additional of the whole element and discretized values. The controller is discrete time, and we leave the disturbance side this way. So this is how we're going to put it in the final form, where yz equals to hgpz dlz over 1 plus hgpz dz plus zgds over 1 plus hgpz. After simplifying, this is the equation we get. This is similar to what before. So the equation 13 yields the discrete time closed loop S-form direct digital control loop, and it's what we call closed loop S-form direct digital loop. So, and you can see the formula. This is also in terms of the characteristic equation that gives some sort of study for stability and its response, as we have done for continuous systems. So very similar. As you can see, the denominator determines the characteristic of the direct digital control loop. as before, and the moves of the usually determine the stability of the closed loop response of DDC loop. For the super control, of course, D0, and for the control of Z. So as a continuous system, and this Z GDDS, we leave it as the Z transformation of disturbance. We don't take it out because DS is not discretized. And if you include the dynamics of the measuring elements, okay, the measuring elements, the GM, and the control loop, then you get a full transfer function for the system. Okay, and you can see the yz equals to the transfer function related to the set point, and yz related to the disturbance. And this is the pulse transformation between CZ output from the controller to YMZ output from the GM.